Okay, so now we're going to take a look at section 3.2, measures of dispersion. How spread out is the data? In the previous section, we looked at measures of the center of the data, the middle of the data, and we had the mean, the median, and the mode as the three things we want to focus on. There are other ways to do it, so there are other ones, but we're not going to look at those in this class. Just be aware that they exist. But for us, we just care about, we're just going to be focusing our attention on the mode, the median, and the mean as measurements of the center. Where's the middle of the data? Okay. On the other hand, we also want to think about dispersion. How spread out is the data in relation to itself, right? So we want to look at ways to do that. And so we're going to be focusing our attention on something called the range and standard deviation. We're going to see how that relates to something called the variance and what it means and how do we interpret that. And then we're going to look at the empirical rule as well as Chebyshev's inequality and see how that all connects to the disbursement of data in a set. How spread out is the data in a set? Okay, up first will be range, the easiest of them all. To order food at McDonald's restaurants, one must choose from multiple lines, while at Wendy's restaurants, one enters a single line. The following data represents the wait time in minutes in line for a simple random sample of 30 customers at each restaurant during lunch hour. For each example, answer the following. What is the mean waiting time? And then find a histogram of each restaurant's wait time. Okay, so let's look at our data. So here's our data. We have Wendy's information, we have McDonald's information. Let's find the mean of both sets. So let's go back to our calculator. And then we got to do the hardest part, which is to insert all those values. Right, so as soon as you hit on, you might be in an unusual screen, a weird screen. So hit clear, quit. It's always a good habit to do that. Then hit stat, enter, and then we have our lists. If you recall earlier, I used this list that was like houses for sale in Nebraska. Okay, I don't need that anymore. So I can go up to select it, highlight the L sub 1, and then hit clear, and then enter. That'll erase all of our numbers. Okay, now on the other hand, let's say I had a bunch of numbers like 7, 13, 5, 9, 2, 3, 6. Let's say I had these numbers and I wanted to delete one individual value. Like I don't want that 9. Okay, I can go up, select it, and then I can hit delete, and that'll erase the 9. If I hit clear, it's not going to erase it. So if I want to erase the 13, I go up to 13 and hit clear, it's not going to erase it. It's still there. Okay? So if I hit clear, if I go up to 13 and I hit clear, it kind of creates that blank for me to type in my new value. So maybe I want to replace it with a 42. And then I hit enter, and it'll replace that 13 by 42. But if I just want to get rid of it, then I hit delete. I have to hit clear, then enter. Do not hit, well, if you hit delete, what's going to happen is you delete the whole column and erase it from the list. So if I hit delete, L1 just goes away. There's no more L1, right? If I hit delete again, I'm just erasing my lists. There's no more lists. I can't find them anymore. Good. So you usually don't want to do that. I'm not really sure what the value of having that delete button is really. So once you've hit delete and they're gone, the way to bring them back is to go back to stat and then go down and hit setup editor, hit enter, hit done. There it is. Now you can go back to stat, edit, hit enter, and they're back. There they are. Okay, so go up, hit clear, enter. That erases everything. You're ready to type. Also, when you start typing your values, make sure that you're down here. This little black box is in the first empty spot, because if you're up there and you start typing in your numbers, 1.5, you're going to get a mistake. Go to error, right? It doesn't like what you just did. Okay? And now it's kind of hard to fix it. Okay, maybe that'll fix it. Okay. Sometimes it's very easy for people to do weird things there, and then, I don't know, just if you get into a weird situation, just come back over here, hit Setup Editor, clear, enter, done, and it just kind of brings you back to the original settings. Stat, enter, there we go. Okay, so now we're going to have to do the hardest part, which is to type in all that information into here. I want one long list for Wendy's, one long list for McDonald's. Okay, so let's type those in. Okay, and 0.23. Okay, so that's definitely the hardest part, inputting all those numbers into here. Make sure that you double check and make sure everything is the same. I think it is. Okay, so you have one big long list for Wendy's, all the Wendy's information, one big long list. I know that it's presented in the form of this table, but you don't want to copy this table onto your calculator. We want to put all of these numbers in one big, long, happy list. And for me, I chose to make this L1, right? So all of this was all L sub 1 is all of this. And then in L sub 2, I put all of the McDonald's information. Again, one big, happy list onto here. Okay, once I have done that, then we can go back to Stat, Calculate, and we still want to do one variable statistics, hit enter, L1, so I'm working with the Wendy's information at this point. Make sure the frequent list is empty. Delete anything that might be on there. Hit delete if you see something. A 1 is a very frequent answer to be there. Delete it. Oops, clear. Get rid of it. And then hit calculate. And here it is. So the mean is 1.39036. So 1.39. Found that the mean for this data, now it's a sample, right? So it's got to be x bar is equal to 1.39. 1.39. Okay, so now let's find the information for McDonald's, which is on list 2. We've got to go back to Stat, Calculate, list 1, hit enter. Now we want the second list. To find the second list, that's going to be right above the 2. But we have to hit the blue button first, second. See the up arrow is blinking, then hit the 2. Now L sub 2 is gonna appear. Don't try and type out L2 by doing L in the green, which is L in the green. Where is it? L in the green, which is right here. Don't try and do L and then the 2. It's not going to work out. We need this L sub 2 in blue. Okay, come down, hit calculate. And look, we get almost the exact same answer, 1.389. 389. Then X bar for the McDonald's information is 1.389. And if we were working with just 2 decimal places, then this would just round to 1.39. And in which case, you wouldn't really be able to tell the difference. So if all we are doing is focusing on the mean time, then they would look the same. But are they the same? Is there anything different about these 2 sets of numbers? Well, the mean is 1.39 in both cases. We did that. But let's say we did a histogram. And again, I'm not going to cover how to do it with your calculator, but let's say we did a histogram. We would see that the histogram for the Wendy's looks like this, whereas the McDonald's information looks like this. Okay, so what is this saying? Remember that the horizontal axis is describing the time values, right? The waiting times, 1 minute, 1.5, 2 minutes, 2.5, all the way out to 5 minutes. And then the heights of these rectangles tell you how frequent that result appeared, right? So there were values in between half a minute and 1 minute. Looks like that's the most common result for Wendy's, waiting between 30 seconds to 1 minute, right? The most, because it's the tallest. A little bit more than 30% of the people that are in our sample had values in that range, right? So there's a lot of people in the half a minute to 1 minute. Let's look at our data. Wait a minute. This is in minutes. In minutes. Okay, so this is more than half a minute, but less than one. We had one value that was less than half a minute. Okay, so, between a half a minute, more than half a minute, but less than 1 minute, we got this result, we got this result, this result, this result, this result. More than half, but less than a full minute. That's this result, this result, this result, this result, right? So all the ones I circled are all the ones that are more than half a minute, but less than 1 full minute. Oh, this one as well. Okay, so all of those circled values are the ones that are being represented by this tallest rectangle right there. There's lots of values that lie in that rectangle between more than half a minute but less than a minute, right? Somewhere in there. Okay, by contrast, if we look at the McDonald's information, looks like the most common one, the tallest rectangle, is this one between 0 and half a minute. So there's a lot of values in there. Put it in blue. There's a lot of values that are between 0 but less than half a minute. Let's go back over here. Let's look at the data from McDonald's. 0 and half. That's this one, 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 this one. Let's include it. That one. That's it. Okay. Oh, no, this one as well. So all these circled blue values are being represented by this tallest rectangle, right? It's showing that a large proportion of our sample values are going to lie on this little region from 0, meaning that there was no waiting at all. You just walked right in and you got service right away, up to this one, which is half a minute. Okay, so that's why it's the tallest. But this is also indicating that there is one extreme outlier over here. Oh, let's put it in green. This guy over here, somewhere between 4.5 to 5 minutes, right? There is somebody over there, 4.5 to 5 minutes. Let's look at the really tall ones. They're 4.5 to 5 minutes. This is 4.5 to 5 minutes. Any other extreme values? That's it. That's that green one. 4.54. 4.54 right in here. There it is. 4.54. That's this person right there. Okay, so even though they both have the exact same mean, both have a mean of 1.39 minutes. I don't know why I did that. A mean of 1.39 minutes. We can tell from the distribution that they're a little bit different, so we need another way of describing the distribution of this data, right? To me, it looks like the Wendy's data is a little bit more clumped up around here. There's a lot of values between half a minute up to, say, 2 minutes. Between half a minute and 2 minutes, these, let's put them in yellow. These 3 rectangles right here really dominate the results. There's a lot of values that lie between half a minute all the way up to 2 minutes, right? So they're more clumped up together around those values. Whereas McDonald's information has one big tall rectangle there, but then the rest of the data is kind of more spread out, right? It's more dispersed, more evenly distributed in this way, whereas this one is more consistent. If one random person goes to Wendy's, there's a pretty high chance that this is how long they're going to wait, somewhere in between here, because that takes up the majority of the results lie in these values. Whereas McDonald's is a little more spread out. It looks like there's a pretty good chance you might have to wait 3 minutes, 3.5, 4, just as much as, okay, maybe only 1 minute. Good. So this data is more spread out than that one. That's what we should get out of it, even though they both have the same mean. Okay, so we need a way of describing this, how spread out the data is. And the first one we're going to think about is something called the range. The range, capital R, of a variable is the difference between the largest value and the smallest value. It's very easy to calculate. Find the largest value in your set, find the smallest value in your set, subtract them in that order, and you'll find the range. Okay, so for example, if we go back to our travel times, this was the startup company that had 7 employees, and this is their travel times. If we take the largest number, which was 43, and the smallest number, which is 5, right? That's our largest number, that's our smallest number. Regardless of how the data is presented, we always take the largest minus the smallest in this order. We subtract them, and we get a 38. That's our range. We describe the range to be 38. And again, that's just one way of describing how spread out the data is. Okay? All right. Okay, now let's take a minute and think about something called MAD. Okay, so this is an acronym, M-A-D, which stands for, the mean absolute difference. Okay, so that's what MAD stands for, mean absolute difference. So let's think about what that is. To do that, let me go over to the side here and think of a different page. Okay, so let's think about the following example. Let's say that I have the following sets of numbers. Set number 1 is the values 10, 10, 10, 10, and 10. 1, 2, 3, 4, 5 different numbers, but they're all 10. Okay, set number 2, let's say it's the numbers 1, 2, 3, 4, and 1, 2, 3, 4, that makes it 8, 10, and 40. Let's say another set of numbers, set number 3. Let's make this one 0, 5, 10, 15, and 20. Okay, so 3 different sets, clearly different sets of numbers, but let's calculate the mean. So the mean for this one is going to come from adding all the values up, and well, they were all 10s. 1, 2, 3, 4, 5, and dividing that by 5. So that's going to be 50 divided by 5. So that's going to be 10. So the mean is 10. Set number 2. Okay, so the mean for this one, same formula. We're going to add them together. 1 plus 2 plus 3 plus 4 plus 40. And divide by 5 because there's 5 entries. Okay, so that gives me 3, 6, 10, 50. Okay, so this is going to be 50 divided by 5, which still gives me 10. The same mean, 10. Okay, what about this one? The mean is equal to 0 plus 5 plus 10 plus 15 plus 20 divided by 5, and they add up to 5, 15, 30, 50. 50 over 5. So the answer is still 10. right? In fact, actually, well, any set of 5 numbers that add up to 50 is going to have a mean of 10, right? So that's an interesting note. So let's say, for example, we wanted to come up with the fourth set number 4. What if you were presented with a question? This is an excellent test question. What if we had negative 10 and positive 5 and 6 and 13? And I said, what is that missing number so that the mean is 10, right? There's 1, 2, 3, 4. There's going to be a total of 5 numbers. So I know that as long as the sum, they add up as long as I know that all of them add up to 50, I'm still going to get that same mean of 10, right? So I know that the mean of this set is still going to be the negative 10 plus a 5 plus a 6 plus a 13. This is negative 5, positive 1, 14. So the number that's missing is going to be 36. If I make a 36 right there, put a 36 right there, then I know that the sum of all of these numbers adds up to 50. Divided by 5, I'll get 50 over 5, which adds up to 10. Good. 95, 1, 14. Okay, good. They add up to 50. All right. So they all have the same mean, right? That was the point of this. They all have the same mean. But they're clearly very different number sets, right? So the question is, how do we come up with some sort of way, some characteristic that can describe the fact that they're different sets? If all you know, right, if all you know without knowing the actual numbers, if all you know is that there's a set 1 and the mean is 10, there's a set 2 and the mean is 10, there's a set 3 and the mean is 10, and there's a set 4 and the mean is 10, well, you'd be thinking, oh, they're all exactly the same, although, as you can see, they're very, very different. Okay, so we need some way of describing the dispersion, how spread out the data is, right? Here, the data is very clumped up. It's the exact same number. Here, it's a little bit more spread out. Here, it's more spread out, and here, it's more spread out. In fact, I want to replace one of these so we can kind of see kind of a middle ground. These two are both fairly spread out. So let's replace one of these guys. Let's replace this guy with another set that also has a mean of 10. It's a little bit more spread out than this one, but a little less spread out than that one. I want some middle ground. How about just the set 8, 9, 10, 11, and 12, right? The mean is still going to be 8 plus 9 plus 10 plus 11 plus 12, all divided by 5. And that's still going to be 50 divided by 5, or 10. Okay, so we need some sort of way, some mechanism that describes how spread out the data is. And one of those ways is, as we noted, MAD. M-A-D, right? The mean absolute difference. The mean absolute difference, MAD. Okay, so how do we calculate MAD? What we're going to do is think about a number line. So here is a number line. And so here is the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Actually, I shouldn't have counted by 5s if I wanted to have that. Let's count by 5. Well, let's count by 2s. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, Okay, something like that. All right, the first set, well, it just has a bunch of 10s in there. 1, 2, 3, 4, 5. Now let's look at the second set. It's a little bit more spread out. So here's 10, there's 8, 6, 4, 2. Over here we have 12, 14, 16. Okay, so we have an 8. So that would be this one. There's a value 8. There was a 9. There was a 10. There is an 11, and there's a 12. Right, this is 10. This is 8, and this is 12. So this one's just centrally located at 10, whereas this one, okay, it's clumped up around the 10. Right, this is a 6. This is a 4. That's a 2. This is a 14. Okay, approximately. It doesn't have to be perfect. All right, so now let's look at the next one. So this is a 10, and I'm going to go to 12, 14, 16, 18, 20, the largest number. And then going in this direction, we needed a 6, we needed an 8, 6, 4, 2, and 0. 0, 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20. Okay, so then we calculate, we have a 0, we have a 5, which is going to be somewhere around there, 15, which is around there, and then a 20. So we can visually see that this one is a little bit more spread out. Finally, the last one. Okay, so this one's really all over the place, so I'm just going to approximate it by saying here is 10. Let's just go to 12, 14, 16, 8, 6, 4, 4, 6, 8, 12, 14. Okay, again, it doesn't have to be that pretty. I'm just pointing out that if we put it on a number line, then it roughly look like this. Okay, so we have a 6, we have a 5, we have a 13, and then we have a couple of really large numbers. So let's put it like way over here, somewhere over here, let's say would be the 36. And then also way over here, below the 0 would be the negative 10. So say like way over there. Here is negative 10. And way over here would be the 36. Okay, what we're going to do is think about the mean, which was 10 for all of them. They all had a mean of 10. So here is the mean. And you know what, it's getting a little messy, so I'm just going to erase this part here. We don't need it anymore. They all had a mean of 10. We already saw that. We don't need it. Let's do a larger one. Equals to 10. Okay, so we're going to take the mean for all of these sets is exactly 10. It's supposed to be a straight line. There it is. Here's the marker, the 10, and the 10. The mean is 10. What we're going to do is we're going to take each one of the values in our set, and we're going to measure the distance away from the mean. So for this first one here, this one was a 6, so we measure this distance from there to there. And then for this one, we measure that distance from there. Think about taking a measuring tape and just kind of going from there to there on the number line. And then there was this one way over there, from there to there. And then there's this one from there all the way over there, right? So these all make up all of those distances, right? We're going to do the same for all of these. So here we have this distance right there, little guy, and then there's this distance right there, another little guy. So they're really kind of small here. a little bit bigger here. So these distances. And then for this one, since they're all at 10, there's nothing even to measure. They're all 10. Okay, so let's think about all these distances. What are they? The distance between 10 and 36. If I took a measuring tape out there, this distance would be a 26. If I took a measuring tape between 10 and 13, this would be a 3. If I took a measuring tape between 6 and 10, that would be a 4. If I took a measuring tape between the number 5 and 10, this would be a 5. And then a measuring tape going down this way. Remember, 0 is somewhere over here. Somewhere around here is 0. So from 10 to 0, that measures as 10. And then you got to go all the way to the other side to get to negative 10. So this would measure a total of 20. Right? A total of 20. Don't worry about signs or anything. We're measuring the distance away from here to here. So the measuring tape would be a 20. Good? Okay. What we're going to do is we're going to take all those distances, add them together, and divide by the number of entries, and that will be the MAD value. So MAD for set number 4, well actually I'm going to put it to the side. For this set, the MAD value, is going to be equal to all those distances. So it's going to be equal to the 20 plus the 5 plus the 4 plus the 3 plus the 26. Add those values together and divide by 5. And I get 25, 29, 32, 58. Divide that by 5. Okay. So double check here. Let's check it. So that's 20 plus 5 plus 4 plus 3 plus 26. It's 58 divided by 5. I'm getting 11.6. 11.6. Okay. Now, that is one way to describe the disbursement of this. What does it mean? On average, each point is 11.6 units away from the mean of the set, which is 10. Right? Don't forget, let's highlight it here. Don't forget that the 10 is the mean. The mean of the set, away from its mean. Okay, so the 11.6, the MAD value, the MAD score for set number 4 here, is one way to describe how spread out the data is, right? All right, let's calculate it for this one. Let's go back over here and get those numbers. Okay, so from 0 to 10, we know that that's going to be 10 units. From 5 to 10, we know that's going to be 5 units. From 10 to 15, we know that's 5 units. And from 10 to 20, we know that's 10 units. Okay? And then there was the 10. From 10 to 10, it's 0. So there's a 0 in there, right? There's a 0 in there because this guy is 0 units away from its mean. Okay, so now let's calculate the MAD score for this set. The MAD score for set number 2 is going to be the sum of all of those values, which is going to be equal to 10 plus 5 plus the 0 plus a 5 plus another 10, and divide that by 5. So we'll get 10, 20, 30 divided by 5, which is equal to 6. So the MAD score for this distribution is a 6. Right? A way to interpret the 6 would be to say that on average, the scores, the individual values in the set, they're about 6 units away from their own mean, which in this case is a 10. Good. But then also it makes it a very nice way to compare, right? Because the MAD score is bigger with this one, right away I know that that means that this set is more spread out because it's got a bigger MAD score. The bigger the MAD score, the more spread out the data is away from its own mean, right? This is all a way of describing how spread out the data is away from its own mean, right? And in this case, the mean for all of these happened to be a 10. Nothing special about 10, I just picked it. Good. Okay, and then this next one, well, this was 8, 9, 10, 11. Okay, we can tell that this is going to be a much smaller result, right? So this one was 8, that's 2 units away from the 10. And then this one was a 9, which means it's 1 unit, right? That guy right there is 1 unit away from the 10. And then the 11 is also 1 unit away from the 10. And then finally, this guy is 2 units away from the 10. So the 8 is 2 units, right, from the, maybe it'll be easier to see it here. The 8 is 2 units away from the 10. The 9 is 1 unit away from the 10. The 10 is 0 units away from the 10. The 11 and the 10 are 1 unit apart. And finally, the 12 and the 10 are 2 units apart. So, it's kind of messy there, but hopefully you get the point. All right, so MAD for this set is going to end up being 2 plus 1 plus 0 plus 1 plus another 2 divided by 5. So we get 3, 6 divided by 5, which is equal to 1.2. Okay, and finally, this last one, well, they were all 10s and the mean was 10. So the distance each unit in the set is away from the mean is always going to be 0. 0 units, 0 units, 0 units, 0 units, 0 units. So the MAD score for this thing, MAD, is equal to, MAD is equal to 0 plus 0 plus 0 plus 0 plus 0, 1, 2, 3, 4, 5, divided by 5. So it's just going to be 0 divided by 5, which is 0. The MAD score for set number 1 is 0, right? So what we're getting out of this is that when you are told that a MAD score is really low, very, very small, that means that the data is really closely clumped up near its mean. Okay, that doesn't mean that the center is a 0, right? Don't confuse that. When the MAD score is very small, close to 0 or even 0, that means that the data is really clumped up around its mean. When the MAD score gets larger, right, the bigger it gets, the more spread out the data is, right? If I told you that there was a new set, if I told you there's this new set number 5, and it's got a MAD score, it's got a MAD score equal to 50, right away I know it's going to be very spread out. Very spread out in relation to its own mean, wherever that is. Good, good, good. So let's think about a little issue here, though. When we were calculating these things, right, I said think about it as like measuring tape. How far do you go from there to there? How far do you go from there to there? Okay, so we were automatically figuring out what to do with the numbers in order to get a positive result, right? So, for example, for these numbers, how did we get the distance between 6 and 10? That 4 right there, well, we got it as 10 minus 6. That gives me the 4, right? I took the mean, and I subtracted the 6, and that's how I got the 4. And that gave me positive 4. On the other hand, over here, how did I get 26? That these are 26 units away from the mean. Okay, well, I took 36 and I subtracted 10. That's how I got 26, right? Oh, okay. But then in this case, the mean is over here. I did 36 minus the mean. And that's how I got to the 26. Good. So in one case, I have the number that I'm trying to work with in our set minus the mean, and in the other case I have the mean minus the number. So which is it, right? If I'm going to lay down a rule, right, if I'm going to write down a rule and say, always take the, here is my set, given some set, x sub 1, x sub 2, x sub 3, dot, 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 all the way out to x sub n. So here is my set. There are n values in my set. How do we lay down a rule so that we always find the distance between that number and the mean? In other words, if I just do this rule, mean minus x1, for example, well, how do I know if that's going to give me a positive answer or a negative one? If x1 happens to be smaller than the mean, then I'll get a positive answer. If x1 happens to be larger than the mean, then I'll get a negative one, right? So we run into an issue when we do this. So in order to avoid that issue, all we have to do is slap it with absolute values. Once we do that, then that makes everything positive, right? So it doesn't matter whether the result in here is positive or negative. Once we do absolute values, then that guarantees that everything will work out well. Good. So let's just lay down a general rule. We want to add them all together. So we want the mean minus x1. Okay, so mean, let's just use x bar. Let's say it's a sample. So we have well, actually, let's work with a population. Let's say it's a population. So it's mu minus x1, and that'll give you that distance of that first number, right? Slap with absolute values guarantees that it's going to give you the distance. And now we want to do the same thing for the next one. Mu of x2, absolute value, plus absolute value of mu minus x3, absolute value. We want to keep going this way, and we want to do that to all the numbers in my set, and we said that there were n of them, right? So let's do this, minus x sub n, like that. What I'm doing here is going to be this. So let's create a number line to kind of visualize this. So if I have a number line, and just for argument's sake, let's just say here is the mean. Right, I'm not actually going to put any numbers on there because I'm just saying in general, just to kind of conceptualize it. Here is the mean, somewhere on that number line. And then the little x values are kind of all over the place. Now, these numbers are not necessarily in sequential order. I'm not saying that they're from the smallest to the largest. They're just kind of given to you. So maybe, like, for example, here's x sub 3. And maybe here is x sub 4. And maybe here is x1. And then here is x2. Dot, 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 right? So there are sub n of these things, right? So maybe x sub n is over there. Good. Okay, so now here is our mean. So we're going to have to find the distance each one of these is away from the mean. So that's what this is going to do. Now the way I drew it, it just so happens that x sub 1 is bigger than the mean, right? Just the way I drew it. Which would mean that in this case, this would end up being a negative, but because I put absolute values, it makes it positive. Good. And then this one would be, okay, well, look, in this case, the x sub 2 happens to be smaller than the mean. It's to the left of it. So this would give me a positive answer anyway. So the absolute values won't hurt. They'll just guarantee that it's positive. Okay, and then we do that for each one of these. So this distance right here is the distance, the absolute value of mu minus x1, like that. And then this distance from here to there is going to be the absolute value of mu minus x sub 4, like that. Good, 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 good. And then this one over here is going to be the distance between those. Is going to be absolute value of mu minus x sub 3. And so we do that for all of them. Once we get them all, right, these all represent the distances that each number is away from its own mean. We add them all together and divide by the number of entries, n, right? There's n of them. And that will give me my result for MAD. MAD is equal to this formula right here. Pretty good. Now, in some places, you might see this formula the other way around, where we just flip around the little x numbers, the little entries from our sample, and the mean inside the absolute values. So it might be this way. But you see that it doesn't really matter. Because we're slapping it with absolute values, it doesn't really matter the order. Either way, whether you get a positive or a negative inside the absolute value, once we apply the properties of absolute values, we guarantee that the result is going to be, whoops, I meant to put it the other way around for this one too. We guarantee that the output is going to be positive, right? Once we apply the properties of absolute values. X sub 3 minus mu, and then x sub n minus mu, absolute value, and then we put an n there. Okay, so this is the formula for MAD, the mean absolute difference. Okay, pretty good. Except we have an issue. When we're dealing with very small number sets and you're kind of calculating it by hand, no problem. Just kind of do it on your own and then figure it out. However, when we're doing it for large sets of numbers, then that becomes problematic, right? The absolute value is not an algebraic property that will help, come up with a shortcut, a way of doing it faster, right? We kind of go term by term and make decisions, right? If this is a negative, then make it positive. If this is a positive, then leave it as a positive, right? So we keep making those decisions. So we need to come up with an alternative to guarantee that it's always positive, but we don't have to actually have to make a decision. We don't have to go term by term and decide whether to make it positive or negative. Okay? One way to do that is to take each one of these things, square them. That guarantees that they're all positive. But then take the square root of all of them, and then that brings it back down. That guarantees that it makes it positive. That's actually one of the math definitions of, that's the definition of absolute value. Okay, so this is what I'm saying. One way to guarantee that all these values are always positive and we get rid of the absolute value is to take this result there and square it. And then once I square it, I also square root it. And this process, the combination of the two, will guarantee that I get a positive result. Okay? So like, for example, think of negative 3. If I square it, I get to 9, and then I square root it, I get to 3. Good? Okay, all right. Well, what if instead of a negative 3 in here, there was just a positive 3? Positive 3. Okay, that makes it 9. Square root it makes it 3. You see that whether you input a positive or a negative, the output is always the positive. Exactly like an absolute value. Okay, so we do that for each one of these things, and we end up with the following. Square rooted, plus, dot, out to the very last one, get x sub n minus mu squared, square rooted, and then we get to that. Okay, so we have a formula for MAD that doesn't use absolute values, right? Absolute value doesn't give you the algebraic properties that we would like to have. It makes it, you have to make decisions on each individual term. It's hard to do several algebraic properties with an absolute value, and other reasons I don't want to get into. Graphs and transformations and properties, it's bad news for us, right? So, okay, this is sort of a workaround, and that works, I guess. Except now it's really ugly. Okay, so instead of doing this term by term by term, as we often do in life, we're gonna settle. We're gonna come up with something that is pretty close, almost the same, Not quite though. We're going to get a slightly different result, but close enough. And the reason we do that is because it ends up being a lot easier to calculate it, for one thing. And then as we further develop statistics, we realize, oh, actually, it works really well. So I don't know if it was one of those necessity is the mother of all inventions kind of thing, and that's why people did this. And then later it turned out that, oh, wait a minute. Upon further investigation, it turns out that it's a pretty good workaround. Okay, so we settle for the following formula. Instead of doing each one individually, actually, let's put it underneath it. We're going to take basically the same thing. We're going to go x1 minus mu and square it. And then x2 minus mu and square it, plus dot, 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 dot. And then all the way out to the last one, xn minus mu and square it, divided by n. Okay, but then instead of taking the square root of each one of these individually, we're going to take the square root of the entire thing. It just makes life a lot easier, and there's a lot of math reasons why that's true, which, we don't want to get into. This stuff is hard enough already. It's an introduction to statistics, so there's good reasons for all of this. But for us, I think it's good enough to say it's a good approximation, and it works really well. Okay? It's not going to be identical, though. This is not equal to this, but it's close. You'll see when we do our calculations that it's actually pretty close. And this is what we call standard deviation. Standard deviation. Now, to further clarify, this is standard deviation of a population, as we'll see in a second. The formula is a little bit different when we deal with a sample. And now that I think about it as a population, actually, I made a little mistake here then. To be consistent with my notation, remember that lowercase n is always referring to a sample. So I should have labeled this with a capital N to be consistent with the fact that we're dealing with a population. That's all. That way just to be consistent. Okay, so what is standard deviation? Standard deviation is a really ugly formula, which is this one. We'll work with it in the next, we'll continue to work with it and see what this equation means and how to calculate things. But standard deviation is an approximation to MAD. It's trying to be MAD. We're settling, right? MAD is what we want. The mean absolute difference. The average distance each number is away from its mean. That's what MAD is. Exactly that. The average distance each number is away from its mean. That's MAD. Standard deviation is trying to be MAD. It's MAD-like, similar to MAD. MAD, close enough. But we should still think about it as a way of describing the mean distance each number is away from its mean, even though it's not exactly that. But it's close enough to that. And as you'll see, there's a lot of great mathematical properties that are unleashed when we work with standard deviation this way. Mean and standard deviation are the two most important characteristics of a population that we're going to be working with. Okay, or characteristics of a sample, whether it's a population or a sample. Characteristics of a set of values, whether they're populations or samples. Those are the two most important things we're going to be working with. Okay. All right, so let's go back to the power. This one? Oh, there we go. Back to this guy. All right, MAD. Let's just write it down one last time for the formula. The formula for MAD, if you're given a set of numbers, so given a set of numbers, x sub 1, x sub 2, x sub 3, dot, 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 x sub n, like that. So there's capital N number of values in my set. Then to calculate the MAD result, MAD, if I told you calculate MAD, what you would do is, well, first of all, you got to go off to the side and find the mean. Okay, so you got to find mu. Mu is going to come from adding all of these. Dot, 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 out to x sub capital N, and then dividing by capital N. That'll give you the mean, right? The mean. Once you find the mean, now you have to find MAD, mean. Okay, so now what you got to do is you got to take the first number and subtract the mean. And then to guarantee we get a positive answer, we slap it with absolute values, plus the next number and subtract the mean, slap it with absolute values, plus dot, 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 keep going. Do that for all the numbers. And so the last number should be this one, minus the mean. Good. So that's the sum of all the distances that each number is away from its own mean, mu. And they're all positive because I did those absolute values. And we're divided by the number of values in my list, which is n. Okay? So this is the MAD result. MAD. The mean absolute difference. This is, on average, how far away are the numbers away from the mean. Okay, but then we settle for an inferior result, right? So, standard deviation. The population standard deviation of a variable is the square root of the sum of the squared deviations about the population mean divided by the number of observations in the population n. That is, it is the square root of the mean of the squared deviations about the population mean. Okay, that's verbally describing exactly what we just figured out. For populations, we're going to use the symbol sigma. Right? It's very important, again, to distinguish between populations and samples. So again, we're going to focus on sigma is the symbol for the standard deviation of a population. And here is the formula, right? Exactly what we looked at before. We take each one of the numbers in our set, x sub 1 out through x sub n. We subtract the mean from each one of those values. We square them all. This guarantees that they all turn out to be positive. We divide it by capital N, and then we take the square root of the giant thing. That becomes sigma, the standard deviation of a population. Now, this is just a shortcut notation to that. Remember that this notation right here, this capital sigma here, represents the sum of. So let me blow that up a little bit. Often we include the little variable, the counter. So I running from 1 to n of, let's say, x sub I, like this. What this is saying is we'll replace the I with a 1, and we get x sub 1, plus, and then replace the I with a 2, so we get x sub 2, replacing that I, plus, and then we just keep going on that cycle, and this guy up here tells me when I'm supposed to stop. I'm supposed to stop when we get x sub capital N. Good. So that's what this notation means. Let's do one more just to make sure you get it. So if we have I goes from 3 to 7, and we have I times 2 plus I squared, say we have that. Okay, then the first one is a 3, so I'm going to take a 3, because the I gets replaced with a 3, and then I'm going to multiply it by 2 plus 3 and square it, right? So I replace the I's with a 3, plus, and now I do 4, okay, so I'll have 4, 2 plus 4 squared, plus, and then I do 5, so it'll be 5, 2 plus 5 squared, and then I do 6, 2 plus 6 squared, and then I do 7, 2 plus 7, and that's when I stop, right? Because the 7 there. Okay, so that's what this notation means. Repeat it, keep repeating it. We replace it by this. We start here, so 3, replace it with 3s. Right, so maybe I should have put them in color, huh? So here is the I and the I. So first we replaced all those i's with a 3. That's where it started. It started at I equals to 3. So 3, then 3. Then we replaced all those i's with a 4. So 4 and 4. Then we replaced all those i's with a 2. I'm sorry, with a 5. Then we replaced them with a 6. Then we replaced them with a 7. And we keep going this way, always adding. That's what this notation means, always adding. And we know when to stop by this number up here. Good, good, good. Okay, hopefully that clarifies it or refreshes your memory on sigma notation. Okay, so that's just a way, this is just a way of expressing this up here. Good, and this is still sigma, right? Population. Capital N is the number of observations in a population. Good, and remember that mu is the mean of a population. So this is definitely the standard deviation of a population. The book covers this. This is a shortcut, right? This is an equivalent way of describing it. We can use our awesome algebra skills to confirm that this up here, that this actually equals this. And you know, back in the day before technology, if we had a huge set of numbers, they needed a shortcut. It was just too difficult to do it by hand using this formula up here, as we'll see in a little bit. So they came up with a great shortcut. This actually makes it easier to calculate it by hand if you have a really big set. Like let's say you have 100 numbers. That's a lot of work. So this makes it a lot easier. However, in this class, we are not going to be using this shortcut. We only have 2 things for us, right? So don't worry about that. We only have 2 things. If it's a small set of numbers, I expect you to do it by hand, like this, or equivalent, like mimic it using your calculator, and I'm going to show you what I mean by that in a little bit when we get to an example. Or at least set it up. I want you to set it up by hand and then use your calculator to do the arithmetic with your calculator, and then that'll be what we do for a small number set, a number set. Now, if the number set is really big, then it's ridiculous to apply this property to a very large data set. So when we want to do a shortcut, our shortcut would just be a TI-84. TI-84 calculator. I'll show you how to do it. That'll be our shortcut. So we are never going to use this shortcut. Don't worry about it. Okay, so here's an example. The following data represents the travel times to work. So we're back to the all 7 employees example. Okay, so this was their travel times. Compute the population standard deviation of this data. So the first thing we have to do is go back and think about what the mean was. So remember, the mean was going to be 23 plus 36 plus 23 plus 18 plus 5 plus 26 plus 43. And all of that gets divided by 7. So the mean is 23 plus 36 plus 23 plus 18 plus 5 plus 26 plus 43 divided by 7, 24.8571. 24.8571. Okay, for the purposes of this, I'm just going to really just round it to 1 decimal place, 24.9, just because it's going to get really messy when I do it. Okay, so now that we have the mean, let's use our formula to find the standard deviation. What we're going to do is we're going to take each one of these numbers and subtract the mean and square them. 23 minus 24.9 squared plus 36 minus 24.9 squared plus 23 again minus 24.9, square that, plus, and then 18 minus 24.9, square that, plus, and then 5 minus 24.9, square that, plus, and then 26 minus 24.9, 4.9 squared, plus, and then 43 minus 24.9 squared. Okay, and now all of that gets divided by 7. So now all of this gets divided by 7. Those are 7 values in our set. And then finally, as a last step, we take the square root of all of this. And that will be sigma. Sigma, the population standard deviation, is defined by this. Very, very ugly. Okay, so it's still 7 numbers. It's still manageable, even if it's ugly. So we could do it. But we do want to take away some of our arithmetic. This is not an arithmetic class, so let's take some shortcuts to be able to use our calculator to do all of this arithmetic. So one of the shortcuts we're going to do is something I like to refer to as column arithmetic. Column arithmetic on our calculators. So this is what we're going to do. We're going to go over our calculator. Okay. We're going to go over to stats, edit, lists. We worked with these before. If I think I'm going to need them again, I would leave them alone. If not, I can erase them. And I think I don't need them anymore. So I'm going to hit clear, enter, go over here, up, clear, enter. Okay, so I'm kind of starting from a clean slate. What I'm going to do is I'm going to input the values of my population onto list 1. So there is a 23, enter, 36, enter, 23, enter, 18, enter, 5, enter, 26, enter, and 43, enter. Okay, so here's all 7 numbers. What I'm going to do next is I'm going to go over to list 2 and I'm going to put down a little equation. Notice that I went up, I use my arrows, use these arrows over here to highlight the L2. Highlight it up here, make it dark. Up here, you can do arithmetic with the columns. So for example, if I wanted to take all the numbers in list 1 and add 5 to them, I would hit second and then L1. See that L1? We get that L1 there. And then I can hit plus 5, enter, and it'll just add 5 to all of these numbers. Right? Okay, so what do I want to do? I want to subtract. Let's go up to L1. Let's hit clear, enter to erase everything. Now let's go up here and I'm going to do L1 minus 24.9. Enter. See, this easily calculates all of these differences. 23 minus 24.9, that's going to be the minus 1.9. And 36 minus 24.9, that's going to be the 11.1. And so on and so forth. So it makes it easy to think about what all those individual results are. And next, I know I'm going to want to square each one of those results. So I'm going to use L3. I'm going to go to L3 and I'm going to click L2 to the power of 2. So all of these individual numbers get squared. And then that makes it easy to be able to work with this equation here. So if you were being asked to write it all down and show your work, but minus the arithmetic at least, then we can use the results from there to simplify things just a little bit. So the next one here would be that sigma is equal to the square root of, oh, wow, that's ugly. Let's say division of, and we have a 7. Okay, the difference for the first one was going to be negative 1.9, and it gets squared. Plus the difference of the second one is the 11.1, and then that gets squared. Plus the next one is negative 1.9, and then that gets squared. Plus then negative 6.9, and then that gets squared. Plus negative 19.9, and then that gets squared. That's this one, 5 minus 24.9. Plus the next one is 1.1, and then that gets squared. Plus the last one is 18.1. The difference between 43 and 24.9. That's going to be 18.1, and then now that gets squared. We're going to square all those, add them together, and then take the square root as a final step. Okay, so again, keeping my work here. L3 was each one of these squared, so I can just copy it right from there. Negative 1.9 squared, that's equal to 3.61, plus 123.21, plus 3.61, plus 47.61, plus 396.01, plus 1.21, plus 327.61. All of that, we add all of those numbers. Once we find the sum of all of those numbers, we divide by 7. And then finally, as a last step, we take the square root of all of those. Good. Okay, well, that's good enough for the, well, okay, let's keep going with the shortcuts. All right, well, now the next step is that we want to add all of these numbers together. Now, we could just take our calculator and just manually type them in there, 3.61 plus 123.21 plus, right, we want to do them all individually. Or we can take our calculator and ask it to find the sum of these numbers. Now, there isn't, to my knowledge, a quick, easy way to just do the sum of all those numbers. Instead, there's just the standard way of finding everything and all you ever wanted to know about list 3, including the sum of the numbers. So we've already done this before. We're going to go over where it says stat, calculate, one variable statistics, hit enter. But this time we want L3, right? Because I want the sum of all the numbers that are on that list, list 3. Go down, make sure that that thing is blank, hit calculate, hit enter, and we get this. Okay, and then the second result here, sum of, remember this little notation, capital sigma means the sum of the x's, the sum of the entries. So this is letting me know that the sum of all of those numbers is 902.87. So that's another way to get this shortcut here. 902.87. So now the sigma is equal to 902.87. That's the sum of all of these numbers. Now we want to take that divided by 7 and find the square root of that thing. Square root of that thing. Okay, so now we can go to our calculator and figure out what that is. So 902.87, let's hit clear here. And it's 902.87 divided by 7, enter. So it's 128.98. So this is 128.98. And then we take the square root of that. And so we take the square root of 128.98, and we get 11.3569. sigma equals to 11.3569. Okay, so the standard deviation of this population of numbers is 11.3569. I want to point out something about accuracy because notice that I've taken a lot of liberty here. Let me go back over here. The mean was actually 24.8571, and then it kept going. I just rounded it off to 4 decimal places, and then I saw, you know what, that's too much work. Let's just round it to 24.9. Otherwise, this would have been really messy, right? If we replaced all these 24.9s with 24.8571s, it would have been really ugly and messy. But okay, so we left it. We already did a big rounding there, right? So we're already very imprecise because we did that. Okay, then I went through and I used my calculator and I round them. And then in some cases, I might have done some rounding in here as well. And then I added it, and then I took the square root, and then I rounded it again. So there's just all kinds of rounding all over the place. As you do your homework, be careful with that because that might be the reason why you get one of the homework questions wrong. It might be just a little bit off based on the rounding. So try and pay attention to the instructions and try and be as precise as you can be. And keep in mind that you get to use your calculator to sort of do this by hand. Right? I don't want you to manually calculate the difference between 23 minus 24.9. That's too much work. And then you have to square it. That's too much work. So column arithmetic simplifies life a lot more. And since we do have the benefit of column arithmetic, then we could be more precise. Right? So if I wanted to find the same results, but I wanted to be a little bit more precise, let me go back to my work over here. Let's go back to, let's clear this. Stat, stat, edit. Let's start all over again. Let's figure out what these are. So clear this, and I want to make it L1 minus, and now let's be a little bit more precise. 24.8571. So it can be kind of ugly little decimals there. Good. Also notice that here it gets cut off a little bit. If you want to be more precise with your answer, the more precise answer will appear down here. Okay. All right, so now I want to take each one of these guys and I want to square them. So let's go to L3, and then this will be L2 to the power of 2. Enter. And now they're all squared. See how it goes out to lots of decimal places for each one of these? Good. Okay, so now we want to find the sum of all of these. So stat, calculate, one variable statistic on L3, calculate. And now we get a more precise sum, 902.8571. So we were pretty close before. 828, okay, so then it was just off by a tiny, tiny little bit. New and improved sigma calculation, sigma, is equal to 902.8571429. We want to take that and divide it by 7, and then we want to take the square root of that. Okay, so clear this. And it's going to be 902, I know, 2.85711429 divided by 7. That's that number. Enter. And then we want to take the square root of that. So second square root is the square root of the previous answer. So instead of typing it all in, I can just say second answer. That little value right there, ans, means the result that came right before it. So that's this one. Good. And then hit enter. Or, just to make sure we're getting the same answer, I could hit square root of and then manually type in 128.8571. 9,7,9,5,9,1,8. Okay, the exact same answer, right? So that second ants is a great shortcut. Okay, so that's my new and improved answer, and look, oh, look, it's pretty much equal to that, right? So it didn't really make a whole lot of difference, but sometimes it makes a tiny little difference, and then that might be off with your homework. So try and be as precise as you can. Again, use column arithmetic on your calculator like this to sort of do it by hand. Right? So even though you're using your calculator to do all that arithmetic and you're doing column arithmetic, I still consider that doing it by hand. Okay, so my new one, well, we've got the same answer even with this one. Sigma was equal to 11.3569. Even with the more improved one, right? Those tiny little decimal things, when we divided it into square root, still didn't make a whole lot of difference. So there is my sigma. So even though you're doing column arithmetic, I still consider this doing it by hand. When the test comes around, if I give you a small number set like this, 7 numbers, and I say, do it by hand, show your work, this is what I expect to see. Something exactly like this. This is doing it by hand and showing your work, even though you didn't actually use, you can use column arithmetic to find these individual values. Good. You can also organize it using a table like we'll see in a little bit in one of the examples coming up. And that will also be a nice way to organize your work. So what do I mean when I say don't do it by hand? Don't show your work. Just let the calculator find the answer. Okay, well, some of you might have already noticed that back when I did this, let's go back to stat, calculate, and then we do one variable stats, L3. Remember, I wanted to find the sum of all the values in L3. Enter, enter. This is how I got the 902.85. Well, if we just notice right below, oops, sorry. I did that to find the sum of all the entries into list 3. However, now if we go to stat, calculate, and go back to the original list, right? All the original values were on list 1. So make sure we go to list 1. Hit enter. And now if we focus right there, there it is. Sigma is equal to 11.3569. So if I'm not asking you to do it by hand and show your work, just use your calculator, then this is how you do it. You put them on a list, and then you do a one variable stats, and it gives you everything you want to know about that list. It gives you the mean of that list. It gives you the median of that list. If we use this arrow, the median, we saw that before. It also gives you the sum of the values on that list. That's what this means. And it also gives you this, sigma, the population standard deviation. Good. So that's our shortcut. Instead of that other more complicated equation that was like a shortcut, our shortcut would just be to use the TI-84. Okay, so let's see what's next for us. Okay, so another way to organize it is with this kind of a thing, a nice table. Good. So this goes right along with what we were doing with our calculator. We can make this list 1. Right, we can make this list 1, make this list 2, which is just the mean, and then we can make L3 equal to L1 minus L2. And then that'll be the difference from each one of these. And then finally, we can make L4 equal to L3 squared. That looks kind of weird. L3 squared. Right? And then that'll give us this. So this is what you find on your final list in your calculator. And then all we have to do is one variable stats, one var stat on list 4, in this case, list 4, if I do it this way. And then that'll give me this. It'll give me the sum of all those entries. And then the last steps to do it by hand would be to just do this. Take that number, divide it by 7, take the square root of the whole thing, and that's how we get our result. Okay, good. All right, so Remember, this is that formula for a shortcut, right? And we are not doing this here. So don't worry about that. Don't worry about that. Don't worry about that. It turns out to be a little bit easier if you're doing it by hand this way. But for us, our shortcut is just to do our calculator. All right, next, what if we're dealing with a sample? The sample standard deviation, S, of a variable is the square root of the sum of the squared deviations about the sample mean divided by n minus 1. So just a couple things that are a little bit different. Instead of sigma, remember sigma is for a population. Right? Sigma is for a population, whereas S is for a sample. So we just use the capital S to represent the standard deviation of a sample. And then the other thing that's different is that we divide by n minus 1 instead of n. Lowercase n is the number of values in our sample, right? So there are lowercase n number of values in our sample. And instead of dividing by that n, we divide by n minus 1. The reason for that is pretty complicated. So it has to do with the following. Back in the chapter on probability, remember when we were choosing things? Like let's say we had the numbers, the letters A, B, C, D, like that. And we were thinking about how many ways are there to organize these. And like, okay, well, we could put the B first, and then the C, then the A, and then the last one. Or we can put the D first, and then the C, and then the B, and then the last one. Okay, so even though there are 4 items that we're organizing, notice that the last one is not really a choice at all. Once we've chosen the B, the C, and the A, there's only one left. So in essence, when you chose the A to go there, you by definition kind of define what the last one was, right? Same thing over here. We made a choice when we put a D first, then we made a choice when we put the C next, then we made a choice when we put the B there, but then the last one, well, it's got to be an A, right? So the amount of variability that we can get is associated with the number of decisions we made. So even though there are 4 items, even though n equals to 4 here, really there were 3 choices that needed to be made, and the last one is just kind of made for you because it's the last one remaining. So we call this degrees of freedom. 3 degrees of freedom. That's why, even though n is 4, 3 does a better job here. That's the other sort of definition or explanation for this. It works, right? It's hard to beat a good thing. In more sophisticated math, as we move forward, we will see that what's happening is that often we have a population, right? And then that population has a population mean. It's got a population standard deviation. From that, we're going to get a sample, right? And then that sample is going to have a sample mean, and it's going to have a sample standard deviation. Okay. We often work with cases where the population is huge, like maybe it's all of California. And then we take a smaller, more manageable sample, like let's say 1,000 people are randomly selected from California. So we hope that the sample is like a little microcosm of the bigger population, but more manageable. So it does a good job. We're hoping that the sample does a good job of representing the population. And so when we find these characteristics of this sample, the mean and the standard deviation, we hope that we can use that information to guess something about the population. Like, for example, if I wanted to find the population, the mean, I don't know, hand width, like if you go from tip to tip, like how wide can your hand grip be? if we did that for every single Californian, how far does it go of every single Californian? That's, I don't know, that's some unknown number, right? But what we can do is we can take a smaller, more manageable sample, 100 people, 500 people, are randomly selected, and then we measure that for everybody. So we might get a result from the sample, I don't know, maybe it is, I don't know, 9.1 inches, just making these numbers up. And now we want to use that to make some sort of inference about the population of all Californians. Is it going to be 9.1? Is that a pretty good guess? We'll look into that. And how confident are we about that guess? Likewise, we want to do the same sort of thing with this. We want to find the standard deviation of our sample, and we want to be able to see if we can use that to get some sort of information about this one. Now, it's not equal to it, so we'll see that what we want to do with that. I don't want to get too much into that, but we want to use this kind of information to make guesses about this and what kind of information can we know from the population if we know the sample. And to get back to this degrees of freedom, we just find that when we divide by n-1 instead of n, we get better results. So the proof is in the pudding. We get better results when we divide by n minus 1 for the sample standard deviation as opposed to n. And then further again, if you ever choose to move forward with stats and go into a more advanced statistics class, you see that there's sophisticated math that backs that up and that confirms and proves mathematically that we definitely want to divide by n-1 for the sample standard deviation. Okay, so hopefully that gives you some sense of why this madness happens. But I could totally understand if at this point you're a little mystified. It is hard. Statistics is a very, very difficult subject. So, you know, sometimes you just kind of have to accept things. You know, I really hate teaching math from that perspective of, you know, here I'm telling you what this is and don't bug me. This is the right answer and just learn it. I'd rather not do that, but it is just the case in statistics. There's a lot of formulas we're going to run into where describing where the formula came from is going to be out of the scope of this class, out of reach for this class. I've given you a little bit of an insight as to why we divide by n-1 instead of n, but it might not be a perfect answer, and that's okay. You're not expected to know much more than that at this level. You just have to know that this is the formula. Okay, so the sample standard deviation is this one, and you divide by n-1, where n-1 is the degrees of freedom for our sample. Okay, again, if you did it for a small number of values, then I would expect this to be done by hand, as we did before, or with the use of column arithmetic. On the other hand, if you have a large number set, your author is going to push you to this shortcut, but we don't use that. For us, our shortcut is just going to be just to use our TI-84 calculator to figure it out. Right? It's just a few buttons away. Okay, so a little this is the explanation I said about the n-1. We call n-1 the degrees of freedom because the first n-1's observations have the freedom to be whatever value they wish, but the nth value has no freedom. This is, as I was explaining with the letters A, B, C, D. When you're thinking about how to organize them, then the first three of them have some level of freedom. There's choice there, there's variability there. But once you make that third spot, the last one is kind of determined. It's whichever letter is left, right? Okay, so moving on. Compute the sample standard deviation of these three numbers. Great. Here's the results of a random sample taken from the travel to work several startup companies. Okay, so the first thing we have to do whenever we want to calculate the standard deviation is to calculate the sample mean. So now this time we got to find x bar, which is going to be equal to 5 plus 26 plus 36 divided by 3, because there's 3 entries. And so x bar is going to be equal to 31 plus 36, or 77. Oh, sorry, 67 divided by 3. which is 22.3 bar. So this is going to be 67 divided by 3, means x bar is going to be equal to 22.3 bar. Okay, so now we take each one of the values in our list, subtract it from its own sample mean. So 5 minus 22.3 parentheses squared plus 26 minus 22.3 parentheses squared plus 36 minus 22.3 squared. And all of that gets divided by the 3, because there are 3 values. 3 minus 1. Remember, it's n minus 1. So here n equals to 3. And then s, the sample standard deviation, will be equal to this whole thing, and then we take the square root of the whole thing. Good? Good. Okay, so there's only 3 numbers, so we could probably easily do it without the use of our column arithmetic, but just to practice, why not? So clear, stat, edit, hit enter. Let's get rid of this old stuff. We don't need it anymore. Clear, enter, go over here, up, clear, enter, over here, up, clear, enter. And now I have 3 numbers, 5, 26, 36. 3 numbers, okay? So next I'm going to subtract, so L1 minus 22 point, and you know, as long as I have my calculator, I can just kind of put more decimals in there. Why not? Be even more accurate. Hit enter. And then I want to square each one of these, so hit L. So that's all of these squared. And next I'm going to want to find the summation of them all, right? But at this point, let me just copy some of these results. It's coming over here. This is saying that my S, my sample standard deviation, is now equal to, let's just stick to 2 decimal places as far as my writing goes. So negative 17.33 squared plus, and then this is going to be 3.67 squared plus, and then this is going to be about 13.67 squared, and then the whole thing gets divided by 2, which is the 3 minus 1, that's 2, and then we take the square root of the whole thing. Okay, next we wanted to square each one, and the calculator already did that for me, so it would be 300.44 plus 13.44 plus 186.78. All of that gets divided by 2, and we take the square root of the whole thing. So we're almost there. Now all we have to do is find the sum of those numbers, divide by 2, take the square root, we're home free. Okay, so back to my calculator. I want to find the one variable stats of L3, and the thing I'm looking for is the sum of these values. So stat, calculate, one variable statistic, L3, second shift, L3, down, down, enter. And then it gives me lots of stuff, but remember to focus on the thing I wanted. I wanted the sum of those 3 numbers, and that's what this is. 500.66667. That's the sum of those 3 numbers. So I'm going to put that over here. So 300 point something plus 13 plus 180. Okay, that seems about right. So they kind of add up to 500.666667, something like that, divided by 2, and then we take the square root of that whole thing. So now I can go back to my calculator and again kind of sort of do it by hand, but use my calculator. Clear, and that'll be 500 point, and there was a bunch of 6's in there, 7 at the end, divided by 2, enter, and then I want to take the square root of that. Second shift, square root of the previous answer, enter, and I get approximately 5 point S is 5.033222957, something like that. Okay, let's confirm that we get the same answer with our calculator. So if I wanted you to do it by hand, the test would say, here are 3 numbers, show your work, do it by hand. This is what I'm expecting to see, right? The setup, and then you did a couple things, and use column arithmetic to get these results. Makes it a lot easier. Okay, but then if I said, don't worry about it, just find the answer. No need to show your work. Okay, well, the easiest way to do that is to go back to our stat. Remember that list 1 is the one that has the original 3 numbers. So we're going to go to stat, calculate, one variable statistics, and now we're going to do L1. Make sure that the frequency is blank, hit enter under calculate, and then notice that right here, S, whoa, way off. What did I do? Something wrong. I'm blaming you guys. 22.3 bar, stat, edit. What did I do wrong? Something's wrong. Okay, 526.36. 526.36. We're going to subtract each one from the mean. The mean is 22 bar. So let's repeat the whole thing. Clear, enter. That'll be L1 minus 22 point, bunch of 3's in there. And then we want to take each one of these values and square them. So L2 power of 2. Okay, that's exactly the same thing. So now let's do stat, calculate, one variable stats, and then we want to do L3. And the sum is 500.6667. Yeah, we did that. Clear. And then we want to do 500 point, a bunch of 6's, divided by 2. That's what I did wrong. Yeah, I don't know what I did before, but it's a bunch of this number divided by 2. We get to 250, and now we take the square root of that number. And we get to 15 point, there we go. I don't know what I did before, but let's erase this guy. So S is actually equal to 15.82192572, and this guy is wrong. So let's erase that right there. Not that guy. So this divided by 2, I think I divided it by 7 for some reason, or I'm not sure what I did. Square root of that whole thing, wrong answer. Okay, so the right answer is this one. And now if we wanted to do it with our calculator and get the simple answer, okay, so we go to stat, calculate, one variable statistics. Now we want to go to L1 because L1 had the original list of numbers. Calculate, hit enter, and there it is. Okay, now it matches. Right? Sample standard deviation equals to 15.82192572, right? Very, very accurate answer. Good. Notice again that the calculator also gives you the population standard deviation for the same set. Your calculator doesn't know whether the set you put into list 1 is a population or a sample. It's up to you to decide. It's up to you to know whether it's a sample or a population, and therefore it's up to you to decide which of these two numbers is appropriate. right? When you're dealing with a sample, it's a sample standard deviation, so this is the result you need. When it's a population, if we were dealing with a population, then this would be the result of the standard deviation of a population. And then both equations have the same formula for a mean. So I know it says x bar, but it's either mu or x bar. Either one is the same thing. Okay, so that's how we do that as far as the shortcut. Let's move on. Let's see what else we got. Okay, so this is the same thing we just did. Right, we go to L1 and we put in our values. Now they take this extra step here of putting the mean, the population, the sample mean into a column. We could do that if we want to. If we did that, we would put this as L2 and just manually type those in there. And then that would mean that L3 is equal to L1 minus L2. Now, if you want to save yourself a step, the way I've been doing it is I don't even bother putting this in there. I can just kind of skip that and go over here, and to get these results, I'm going to do L2 equals L1 minus the 22.3333, right? I put it in there. Either way is fine. And then next, I want to take each one of these results and square them, so I make L3 equal to L2 squared. And that's what goes into here. So we get that, and now we do one var stats, one var stat on L3. And then that's how we get our whole breakdown. The calculator will give us x bar. It'll give us, remember, x bar would be the mean of list 3. That would be the mean of these numbers. We don't want that. But we do want the sum of these numbers. The second result when we do one var stat L3 will give you the sum of these numbers, and we'll get this result right there, 500.66667. And now we stick that in there, divide it by 2, take the square root of the whole thing. That's how we get to the numbers 15.82. Okay, again, the author, the book, will push you to this shortcut, which we do not use. Don't use that shortcut. It's just more trouble than it's worth. For us, our shortcut is just our TI-84 calculator. Okay, determine the standard deviation wait time for Wendy's and McDonald's, which is larger and why. So remember that we had these two lists of values, and now that I think about it, I should have deleted them. So let's type them in again. So let's go to stat, clear, stat, edit, hit enter. And let's delete these things. I'm not going to need them. So clear, enter, go to the right, up, clear, enter, go to the top, to the right, hit clear, enter. Okay, so obviously there's a lot of numbers here. It would be cruel and unusual punishment to say, here, find it by hand, right? So if I ever ask you on a test to say, find the standard deviation by hand, show your work, we're going to be dealing with a very small number set at that point, like 4 numbers, 5 numbers. This one is just massive. To do this whole thing by hand would be rough, right? So let's use our calculator. So we're going to put all our results onto list 1 for Wendy's. So let's go over to L1. I'm going to type in all of those numbers for L1. So 0.50, 2.53, 1.88, 3.99. Okay, and 0.23. Okay, so I've very painfully, manually inputted each one of the values for Wendy's and McDonald's. So all of the Wendy's information is on list 1. All of the McDonald's information is on list 2. And yes, you have to do this. And yes, it's annoying. And no, there's no way around it. Statistics is annoying. Okay, so you might want to double check and make sure that they match up and you didn't make any mistakes. Luckily, we also have the answers, so if we do make a mistake, we can confirm that something is wrong and come back and double check things. But they look pretty good to me on initial inspection. Oh, do we have a 99? 1.2. 1.2, 0.99, 0.72, 0.67, 0.9, 0.84. Yeah, okay, I think that's right. 23, 1.7, 1.5. Okay, I think that they're about right. Okay, so next we're going to find information about list 1 and list 2. So we're going to do stats, calculate, one variable stats. Let's do it for the Wendy's information first on list 1. Hit enter, calculate. Okay, so we have the mean, 1.39. I think we've seen that before. The mean waiting time at the Wendy's was 1.39. And then standard deviation. Now, is this every single customer that has ever gone to Wendy's? No, obviously not. It's a sample of 30. So we would use the sample standard deviation number, 0.7384. Right, so you always have to ask yourself, am I staring at a set that represents the population? Is this all of them? Or is it a sample from the population? Right, so we have the sample standard deviation as 0.7384. Let's write that down. We have that the mean, x bar, was 1.39, and that the sample standard deviation, 1.39, round it to 1, I guess. 391, and the sample standard deviation is 0.7384. Good. Okay, so now let's get the information for the McDonald's. And I believe that the McDonald's had the same mean. So I was on L2 now. Second shift, L2. Enter, enter, enter. So basically the same mean, 1.389. So they both kind of round to 1.39. And the standard deviation is a little bit different. So now for McDonald's, x bar is 1.3893. So it's approximately close to 1.39, kind of rounds to 2 decimal places to the 9. And this one, again, rounds to 1.39, so they're basically the same mean. But the standard deviations, the sample standard deviations, are very different. For this one, we get a 1.2649 approximately. For this one, we get a 0.7384. Okay, let's make sure that that matches up with the results the author got. About 3.8, okay, that's good. And then 2.265, okay, so the same results that the author got. What do we make of that? Okay, so how do we interpret that? Remember, standard deviation is attempting to talk about MAD, the mean absolute difference. So that's how we can think of it, even though it's not exactly that. So MAD is the average distance each number is away from its own mean, right? It's a measure of how spread out the data is. The bigger it is, the more spread out it is. And the smaller the value is, the closer to 0, the more clumped up the data is around its own mean. It's not clumped up around 0, it's clumped up around its own mean. The more consistent the numbers are. Okay? So that's what we can get from this. This number is close to MAD. We can think of it as MAD. It's not exactly going to be MAD, but it's approximately the average distance each one of these numbers is away from its own mean. And this one means, again, the average distance each one of these numbers is away from its own mean, where this is the mean for this set, and, well, they both have about the same mean. Okay? So, very often, the way we use standard deviation is to compare between 2 different sets. Just by seeing that the standard deviation for the McDonald's information is bigger, almost twice as big as that one, a lot bigger really, I know that there's a lot more variability in the McDonald's. It's more spread out. Wendy's is doing a better job of being consistent. So you got to ask yourself, what is better? Being more consistent or being more spread out, right? So when you walk into a McDonald's, you randomly go into McDonald's, you might end up with a very low number. Look, there's several zeros. 0, 0 time. Yeah, you didn't wait at all. You just walked in and there was no line, just walked right up to the register, zeros. But you might also walk in there and have to wait 4.5 minutes before you get up to the register. That's big, right? On the contrary to that, Wendy's, nobody ever waited 0. It's impossible. None of these people ever walked in and there was nobody waiting. So there was always some amount of waiting. But the waiting is a little bit more consistent near its center. That's what that means. Because the standard deviation is smaller, it means that all the data is more clumped up around its mean. So there's less variability. There's more consistency with the Wendy's, more variability with the McDonald's. That's how we can interpret it. And both of them, again, are attempting to be MAD, are attempting to describe MAD, the mean absolute difference. So it's a measure of dispersion. How spread out is the data? It's attempting to give you approximately how far each number is away from its own mean. Okay. So that's a really important concept, so I think I'm just going to do one more visual exercise to describe the same thing. So if we go back to our number line, remember our number line? If we had a giant number line here, and we had the mean, okay, the mean is right here at 1.39. Here's our mean. And then that first number on the list is 3.5. Let's say that 3.5 is over here, 3.5. Okay, we want to find the distance this number is away from its mean, right? That distance right there. So 3.5 minus 1.39, 3.5 minus 1.39. So that we get the 211, 2.11. Okay, the next number on my list here for McDonald's is way over here. It's a 0. So that's a 0. And again, we want to find the distance from 0 all the way to there. So then that'll be 1.39. Okay, the next one is 1.97. So that would be like around here somewhere. 1.97. Good. So again, we want to find that distance away from its own mean. This. So 1.97 minus 1.39. That gets me to 0.58. Okay, and we want to keep doing that. Dot, 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 dot. Keep doing that for all of them. And then we add up all those numbers, and that's how we find MAD, right? Remember MAD? MAD is going to be equal to the 2.11 plus the 1.39 plus the 0.58 plus dot, 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 dot for all of these, right? Of course, I can't do them all. For all of these, add them all up together. When you're done with all that, we divide by the number of entries, of which there are 30. And then we divide that, and then that'll be our MAD value, the mean absolute difference. So it's a measure of, on average, how far away are the numbers away from its own mean. The mean distance that, if we take all the distances of each number from its mean, find all those distances, and then find the mean of that. The average distance each number is away from its own mean. That's MAD. And standard deviation of this, it's trying to be MAD, close to MAD. It's imitation MAD. Okay. All right. So we had the 2. So recall earlier that the data is more dispersed for McDonald's, resulting in a larger standard deviation, right? So larger standard deviation means it's more diverse, more spread out. Smaller standard deviation means that the values are more clumped up together. Okay, we're going to look at something else called the variance. The variance of a variable is the square of the standard deviation. So all you have to do is find the standard deviation and square it. Well, the formula for the standard deviation involves a root, right? So if we have the formula for this guy is going to be to take each number and subtract it from its mean, square it, plus the next number, subtract it from its mean, and square it, dot, 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 out to the last number, x sub capital N minus mu, square it, divide the whole thing by n, and then take the square root of the whole thing, right? This is the formula for the sigma, the standard deviation of a population. But now sigma squared equals the variance. We take this and square it. Well, if we square it, it'll undo this square root process. So it's really just this part in here before we take the square root. That's what variance is. So variance is just going to be x1 minus mu squared plus x2 minus mu squared plus dot, 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 and then x sub n minus mu squared, the whole thing divided by n. And that's what variance is. Now, when we're dealing with standard deviation, we say that that's approximately mad. It's trying to be mad. It's trying to describe for you the distribution. It's approximately the mean distance that the values are away from their own mean. So we can kind of visualize what standard deviation is. How do we visualize variance? Well, we can't. And it doesn't really have any direct application to our sample. But why do we care about variance? Well, okay, let's go back up here when I was describing the reason we care about the population versus the sample. Remember this up here? So we will always have some population. Usually it's some very large population or some population that is very difficult to work with for some reason. Okay, and that population has a population mean and a population standard deviation. Okay, we're going to take a sample from that, hopefully a nice random sample, hopefully large enough, so that hopefully this sample is a good representation of that population. It's like a little microcosm, right? It does a good job of representing the population. And then we are going to find the sample standard sample mean and the sample standard deviations. We want to be able to say something about these unknown values based on the sample information we find. And through sophisticated math, as we will see, it turns out that this is a really good guess for that. So like if I wanted to figure out the mean height of all Californians, that's millions of people, I could just take a sample of, say, 1,000 people, a little more manageable, find the mean height of those 1,000 people, and that answer will be a very good guess for this one. Okay? Now for standard deviation, if I wanted to find the sample standard deviation of the same thing, we have 1,000 people, let's find their heights, let's find the sample standard deviation, and I want to use that to give me a guess about this, well, it turns out that that's just not quite there. It doesn't do a very good job of that. But we have found that instead, s squared does do a good job of guessing sigma squared. So the variance is necessary for that. It does a good job of helping us guess what this is based on our sample. And once we have a pretty good guess what the variance is, well then we know that we just take the square root, and then that's how we get to the population standard deviation. So again, it's one of those things where we created something because it was useful. And we do have the math, the sophisticated math, to prove that that's what does, the best job. But all that stuff is out of the scope of this class, so you don't have to worry about the math to prove that this is true. I just wanted to give you some sense of why we care about variance. right? That's really the only reason why we care about variance. And it's very easy to calculate. You just have to find the standard deviation and square it if it's given to you. Or if you're calculating it, just don't do the square root. And that's how you find it. Okay, all right, so back to over here. The following data represents the travel time. So we're back to the travel times of the 7 employees. Compute the population and sample variances of this data. Okay, well, we've already done this stuff by hand, so let's go back to using our calculator. So let's go back to stat, edit. I'm going to use L, just for fun, I'm going to use L4. Doesn't matter as long as you keep track of them. So I need 23, enter, 36, enter, 23, enter, 18, enter, 5, enter, 26, enter, and then finally 43, enter. Okay, so here are my results. 1, 2, 3, 4, 5, 6, 7 on list 4. Let's do stat, calculate, one variable stat on list 4. Enter, enter, calculate, and I get everything and all I ever wanted to know about list 4, including the standard deviations. So the sample standard deviation and the population standard deviation. Remember, the calculator gives you both. It doesn't know what you're working with. It's up to you. But in this case, it said to do both. So I'm just going to set it up so we can see what the setup would have been, and then I'm just going to jump to the punchline and write it out. So for the, if this was considered to be a population, if it was considered to be a population, then, let's go over here, then the mu would be 24.8571, which means the mu, let's just round it to about 24.9, right? And then the setup for the standard deviation would be, standard deviation is equal to each one of these numbers, 23 minus the mean, 24.9 squared, plus 36 minus 24.9 squared, plus dot, 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 right? We're going to insert the rest of those. The last one is 43 minus 24.9 squared, and then we divide the whole thing by capital N, which means that there are 7 entries, and then we take the square root of the whole thing, and that's the standard deviation. And I can see from my calculator that that means that the standard deviation is equal to 11.3569. All right, so then all I have to do for the variance is going to be to square that. So the variance, right, the notation for it is really just to do that. That is variance, right? There is no special letter to indicate variance. It's just sigma squared. And so sigma squared is going to be equal to 11.3569 squared. So we get 11.3569 to the power of 2. We get 128.9797992. Okay. On the other hand, it says compute the population and sample all 7 inputs to work and sample variance. Okay. On the other hand, if we were thinking of this as a sample, I think that's what they mean here. So now, if this wasn't a population, this was a sample. Now, if this was a sample, then that means that the mean would be exactly the same as before, 24.8571, but we would, let's just approximate it to 24.9. Okay, and now the sample standard deviation, S, would be each one of these values. So starting with 5, I believe. no, 23. So 23, 36, so it would be 23 minus 24.9 squared. It would be 23 minus 24.9 plus the next one, 36 minus 24.9 plus the next one, dot, 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 keep going in the same fashion. And then the last one would be that 43 again, 43 minus 24.9 squared. And then because it's a sample, we know we divide by n minus 1. So in this case, we divide by 6, not 7. And then we take the square root of the whole thing. And when we do all of that, we're going to end up with this answer. That's where the 12.2669 comes from. And now to find the variance of the sample variance is equal to s squared, which is equal to 12.2669 squared. Okay, so that is equal to 12.2669 to the power of 2 is equal to 150.4768. 4768. Okay, so there they are. If it's a population variance, this was a population, then this would be the population variance. If this was a sample, if you thought of it as a sample, then that would be the sample variance. Mm, 11.36 squared. Okay, so we get that. And then 15 point, uh-oh. How come you got the 15? 15.83 in the standard. Oh. Ooh. Fail. Happened. 15.83. Didn't we calculate? I think I misunderstood something here. Didn't we calculate a sample standard deviation up here? Yeah, okay. So I misunderstood, sorry. They didn't mean, oh, pretend that the 7 numbers are actually a sample from a larger population. They meant go back and think about the specific sample from up here where we found the standard deviation of these 3 numbers, which is the 15.82. Okay, so we already found that standard deviation, which is this guy. And then to find the variance of this, variance is equal to s squared, which is the 15.82 squared. 15.82 to the power of 2 is equal to 250. 250.2724. So they're getting it from here. So sorry, I misunderstood this statement here. So what I thought they meant was, here are the 7 numbers. It's a population. Calculate the population mean, population standard deviation, now population variance. We did all that. I thought they meant now think about this as a sample. Pretend it's a sample from a larger population, and now calculate its mean, its sample standard deviation, and therefore its sample variance. But that's not what they meant. That wasn't the intention. They meant the sample was go back to that sample from before, which was 3 numbers, right? It was the values where is it? It was the numbers 5, 26, 36. Our sample using sample 5, 26, and 36 from above. Well, we already did this kind of work above there to find the standard deviation, and that's how they are getting their results. So using that sample and the work from before, we can just get to this. Right? From before, we saw that the sample standard deviation was 15.82, so its variance is going to be 150.27. That's just this number squared. And then 11.36 is the standard deviation for the population. And so its variance is going to be this number squared, 129.05. Okay, almost done with this section. The empirical rule. So if a distribution is roughly bell-shaped, approximately bell-shaped, then the empirical rule says that approximately 68% of the data will lie within one standard deviation of the mean. That is, approximately 68% of the data will lie between mu minus 1 sigma and mu plus 1 sigma. Approximately 95% of the data will lie within 2 standard deviations of the mean, or approximately 95% will lie between mu minus 2 sigma and mu plus 2 sigma. And finally, approximately 99.7% of the data will lie within 3 standard deviations of the mean. That is, 99.7% of the data will lie between mu minus 3 sigmas and mu plus 3 sigmas. Okay? We can use the empirical rule based on sample data with x bar used in place of mu and s used in place of sigma. Okay, so this is a nice little diagram that describes exactly all of that. I know there's a lot to take in, but this little picture describes the whole thing. So we have the mean of our distribution, and if we add to it a distance of 1 standard deviation, 1 sigma, we get to this value. And if we subtract 1 standard deviation away from its mean, we get to this value. And so the empirical rule says that approximately 68% of the data within 1 standard deviation will lie between there. Remember that when we see a graph like this, the horizontal values tell us the values, whereas the height tells us how frequently that value is observed. We can imagine this as a bunch of like little ping pong balls that have little numbers. Like let's say that the mean is, I don't know, 24. So you can think of this as 25 right next to it. And there's a little ball that has 25, another little ball, another little ball, another little ball, another little ball. They all have 25s. So the fact that it's really tall tells me that there's a lot of this number, right? And then way, way over here, it's not very tall. So let's say way over here, we have the number 35. There's not that many little balls that have 35 on them because it's not very tall. Okay, so you can kind of visualize that, except that the balls, there's an infinite number of balls here, because this could be a 25, and then right next to it could be a 25.1 or 25.01. So in actuality, we really can't actually put little balls there, but you can visualize it that way. Right, so the horizontal axis tells you the values we're dealing with, whereas the heights of this tells us how often we observe those values. The taller it is, the more frequent we see it. So in a nice bell-shaped distribution that's symmetric like this, the most commonly seen values will dance around our mean, right? So that's what the empirical rule says. If we have a nice bell-shaped distribution, about 68% of our observations will be within 1 standard deviation, mu minus a sigma, mu plus a sigma. About 95% of our data will be within 2 standard deviations, right? Minus twice sigma, plus twice sigma. And about 99.7% of our data will be within 3 standard deviations. Good. And also we can kind of break those percentages down this way. 34 and 34 is the 68. And then we can figure out the rest this way. Okay, so when you do your homework and you're dealing with empirical rules, this is a really nice image, graph to refer back to. Here's an example. The following data represents the serum HDL cholesterol of 54 female patients of a family doctor. Here they are, all 54 values. So let's compute the population mean, the standard deviation, draw a histogram to verify the data is bell-shaped. Okay, so we can recall how to do that from before. Let's go to our list 1, type in all these numbers, do a one variable stat, and then we'll get both our mean and standard deviation. So I'm just gonna jump to stipulating that. So here they are. If we did all that work with our calculator, we would find the mean and the standard deviation. Also, if we created a histogram, we would see that it looks a little something like this, approximately bell-shaped. It's not perfectly bell-shaped, but it's pretty close, I think. It kind of follows roughly this sort of shape. So we can approximate it to be about bell-shaped, even though things aren't perfect, right? We'll find that in life, rarely is anything exactly perfect, but close enough is often good enough. Okay, the next part of our question, though, says, determine the percentage of all the patients that have serum HDL within 3 standard deviations of the mean according to the empirical rule. So according to the empirical rule, 97, what did it say, 90, what percentage are within 3 standard deviations according to the empirical rule? Well, according to the empirical rule, it should be about 99.7. That's almost all of them. It should be pretty rare that we don't find one. So if we go back 3 standard deviations below the mean and above by 3 standard deviations above the mean, we should be able to find an interval that hopefully captures almost all of the data, 99.7. Okay, so let's go back over here. If we know that the mean is 57.4, then we need to find the number that is mu minus 3 sigma. Mu minus 3 times the sigma. So it'll be 57.4 minus 3 times 11.8. Okay, so let's figure out what that is. That'll be 57.4 minus 3 times 11.8. That gets me to 22. 22 is over here, somewhere around here, say, 22. And it is a number that represents, where's 50? The mean is somewhere around here. This is the mean, which is 57.4. So this number, 22, represents 3 multiples of sigma, right? If I measured 1 sigma, which is 11.8, and then I measured another sigma, which is 11.8, and then I measured once again 1 more sigma, which is 11.8, these 3, we subtract that much from our mean, we get to this level, 22. And now we do the same in the other direction. We need to find mu plus 3 sigma, which will be 57.4 plus 3 times 11.8. And that'll be 57 plus 3 times 11.8. This equals 92.4. 92.4. So this number over here, 92.4, will be a value that is approximately 3 sigmas to the right. So if we go this way and we measure 11.8, and then we measure again another 11.8, and then finally we measure one more time, another 11.8, we'll get to the mean plus 3 sigmas. That's 92.4. And mu minus 3 sigmas, that's 22. So the space between 22 and all the way out to 92.4 should capture, according to the empirical rule, 99.7% of all the data points. if it's approximately bell-shaped. And it seems to make sense according to my picture. Almost everybody is in there. Everybody, if not almost everybody, is in there. Okay, so what we could do is actually physically go through our numbers and see if any of them are below 22 or above 92, right? So there's 22 and above 92.4. Are there any values that are really big or really small? I don't think there are any. Nope. So at the moment, I have all of them. All 54 are inside this zone. So at the moment, I have 100. I have 54 out of 54 numbers lie in this range, or 100% of them from my sample, which is in line with my empirical, or the empirical said about that. It didn't say it was going to be exactly 99.7. It just said about that, right? So 100%, close enough. It's close to what we expect. Okay, so again, if we refer to this, according to the empirical, about 99.7% of all patients will be within 3 standard deviations. We already figured that out. Okay, part D, the next part. Determine the percentage of all the patients that have serum HDL between 34 and 69.1. Okay, so let's see. Remember that our 34 and 69.1. Going back to this guy here, now let's do the same thing, but except instead of doing 3 sigma, let's kind of reverse engineer this here. So we wanted 34 and 69.1. Okay, erase these things. It's too much. Okay, so the mean is still 57.4. Let's think about the gap, the space that happens between 34. So let's say here's 34. Let's find that space right there. So let's subtract it. So that would be 57.4 minus 34. 57.4 minus 34. That's equal to 23.4. 23.4. And then if I take that number and divide it by the standard deviation of 11.8, 23.4 and divided by 11.8, divided by 11.8, I get really close to 2. Really, really close to 2. 1.983, which is really close to 2. So another way to interpret that is that the 34, that's 4, is almost 2 sigmas to the left. Really close, right? So if I go this way and measure that way, 1 sigma below the mean, remember the sigma was 11.8, and then we go a little bit more, and that's approximately another. This is 2 sigmas below the mean. It's approximately mu minus twice sigma, right? It's approximately equal to 57.4 minus twice 11.8. Pretty close to it. Okay, what about the other number? The other number was 69.1. That's this guy right here, 69.1. Again, let's figure out what that distance is. The distance between the mean and the 69.1. So let's subtract them. 69.1 minus 57.4. 69.1 minus 57.4. That gets me to 11.7. And then again, that's really, really close to 1 sigma. right? So if I divide it, 11.7 divided by 11.8, it's really close to 1. Okay, so this is really, really close to 11.8. And remember the 11.8s, those are sigmas. So I went 1 sigma this way, 2 sigmas that way. And then if I go in this direction from the mean, I go 1 sigma in this direction. So in other words, that means that this guy is approximately equal to mu plus a sigma. Approximately equal to 57.4 plus 11.8. Close, right? Again, not exactly, but pretty close. So we're saying that between 34 and 69.1, and then the mean is right here at 57.4, that this number is mu minus 2 sigmas, and this number is mu plus 1 sigma. So if we look at our distribution, this is the mean. If we go out 1 standard deviation, 2 standard deviations, this is mu minus twice sigma is this point. So if we add the 34 and the 13.5, we'll figure out approximately what percentage of our values will lie in this zone between this number and that number. And if we go out to 1 sigma, mu plus 1 sigma, we see that 34% of our data lie in there. So going back to our actual numbers, for us, the numbers were 34. 34 was 2 standard deviations below the mean, which was 57.4. And 69.1 is this one, was 1 standard deviation. So that means that if we add these three things, 68 plus 13, so 81.5% of the data should lie between these two numbers, right? That's why we add this one plus this one plus this one to get our answer. Okay, and finally, determine the actual percentage of patients that have a serum level between 34 and 69.1. Okay, well, we found the theoretical answer. In theory, based on the empirical rule, we would expect that about 81% of our 81.5% of our results should lie in this range. Let's highlight it. This range right here, from there to there, should be about 81.5%. But now in actuality, what am I actually seeing in my results? Okay, to get that answer, we're going to have to go back to our actual table of values. Here it is. And count how many of them lie between 34 and 69.1. 34 and 69.1. So this one, and 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 this one, not that one, this one, just barely, yes, 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 no, yes, just barely, yes, 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 no, yes, yes, just barely, yes, no, yes, 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 no, yes, 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 no, no, yes, 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 no, yes, 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 no, yes, yes, and yes. Whew. Okay, so how many are there total? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45. I get 45 out of the 54. 45 out of 54. If we divide that, we get 45 divided by 54. I'm getting 83.3 bar percent. All right, well, pretty close to our theoretical answer, right? We've said that should have been 81 approximately. Whoops. Should have been 81.5, but we've physically counted our results and we got 45 out of 54. When we divide those two, we get 83.3. That's the actual observable results from our sample. And we compare that with our theoretical result by the empirical rule, right? And again, that's because it's assuming that our distribution is approximately bell-shaped. Good, 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 good. Almost done. Last concept in this section, and that's Chebyshev's inequality. Okay, so Chebyshev's is very, very similar to the empirical rule, except the empirical rule only applies to distributions that are approximately bell-shaped. If it's approximately bell-shaped, then we get these kinds of results. And I've made it all messy here, so let's go back up here. This guy. So this is the empirical rule, and it only applies if the distributions are approximately bell-shaped, right? They kind of do this. But what if they're not bell-shaped? Lots of distributions are not bell-shaped. Let's say, for example, it might look like this. Maybe it kind of comes up really fast and then slowly goes down. That's not exactly bell-shaped. Okay, even worse, what if it's got two humps? What if it goes up, there's a very popular thing there, comes back down, and then there's another very popular thing there, and then goes back down? That's definitely not bell-shaped. Or what if it's just consistent? It's just always about the same, right? So we have something like this. We'll get more into these kinds of distributions later. I'm just pointing out that there's lots of different distributions out there, not just the bell shape. And the empirical rule only applies to bell shape. So what if it's not bell shape, just some distribution in general? Well, that's when Chebyshev's inequality comes true. So for any set of distribution, any set of data or distribution, it states that at least 1 minus 1 over k squared percent of the observations lie within k standard deviations of the mean, where k is any number strictly greater than 1. So it doesn't work for 1. Starting at 2, for example. Well, we usually like to stick to whole numbers of k, at least in this first section. So you can think of it as 1. But anything strictly greater than 1 is what we're looking for. Okay, so that is at least 1 minus 1 over k squared percent of the data will lie between mu minus k sigma plus mu plus k sigma, for k being strictly greater than 1. Good, good, good. Okay, so let's use Chebyshev's theorem to go back to our previous example. Part A, determine the percentage of patients that have serum HDL within 3 standard deviations of the mean. Okay, so if you remember, the mean was 57.4. The mean of patients, so this would be x bar, is equal to 57.4. And then the standard deviation of our patients, S, was 11.8. So if we're doing within 3 standard deviations, we're going to go above and below by multiples of 3 multiples of the standard deviation. So that would be 57.4 plus 3 times 11.8. That'll get me to the 92.8, I think. 11.8 times 3 plus 57.4, 98.3, okay. And if we do 57.4 minus 3 times 11.8, we get to the 22. So check that. 57.4 minus 3 times 11.8, 22. Okay, so on that number line, here is the 57.4 in the center, and we want to go all the way out here to 22 and all the way up here to the 92.8. This represents within 3 standard deviations of the mean, right? Within 3 standard deviations of the mean. Okay, so if this was a bell-shaped distribution, if this thing had a shape that kind of went up like that and came back down and was approximately bell-shaped, then we would use the empirical rule that we did before. But if we have no idea what this shape looks like, we don't have that information, then we're going to have to settle for Chebyshev's inequality, which says that we should have at least the percentage from that equation, right? So the equation was 1 minus 1 over k squared times 100%. So in our case, we're going this way by multiples of 3. So in this case, k equals to 3 because we want to be within 3 standard deviations. So that's where this came from. It's the mean x bar plus or minus 3 times the standard deviation. That's how I got the ones below and the one above. And so for us, k is equal to 3 within 3 standard deviations. So that's the k that goes right in there. Okay, so from there, I'll get that this is 1 minus 1 over 3 squared times 100%, which is going to be 1 minus 9 times 100%, which is then equal to 8/9 times 100%, which is then going to be 88.88%. Just to kind of round it to the nearest whole number in this case, let's say about 89%. Okay, so Chebyshev says that we expect at least this percentage or more. Right, so it's not going to be exactly 89. It might not be close to it, but we're putting a lower bound on what we expect to see. Okay, so notice that's what the Chebyshev says. For any data set distribution, at least 1 minus 1 over k squared % of the observations lie within k standard deviations of the mean, where k is any number greater than 1. Okay? So, good. Okay, so now for part B, it says, determine the actual percentage of patients that have a serum HDL level between 22 and 92.8. So for that, we're going to have to go up to our actual data points. Let's go back up to these guys. And we want to figure out how many of these numbers actually lie in that range. So we have 22 all the way out to 92.8. And I think in this case they all do. Anything below or above, no, not there. Below or above 92. No. Below or above 92. Below or above, below or above. Below or above, below or above, below or above. Nope. Okay, so here's a case where all of them, all 54, are in this range between here and here. 54 out of 54, or I'm getting 100%. That's okay. That doesn't contradict Chebyshev. Chebyshev says at least that result. We got an 88 from Chebyshev. So it said that the number of observations should be 88% or more. So 100% is definitely more than 88%. So it's consistent with Chebyshev's. Okay, that's the end of section 3.2.